charge carriers takes place in semiconductor. Next, we will see the topic diffusion. What is a diffusion is. So the diffusion basically this diffusion is the phenomena in taking place in semiconductors. It will be such that whenever the charge carrier concentrations difference is there with respect to distance inside a semiconductor material. So if charge carrier concentration is different at different places, then because of this difference in charge carrier concentration, there is a movement of charge carriers from high concentration to low concentration. Okay, so that is basically defined by the diffusion process, and this diffusion process results in a current because the charge carriers are flowing from one location to another location. So because of this movement of charge carriers, because of diffusion, there is a current called diffusion current. So what is the formula around what parameters this diffusion current will be depending? We will see that. So first of all, we will see what is diffusion. So basically here in semiconductors, because of the non-uniform the charge carrier concentration throughout the semiconductor structure. So suppose okay, so basically in semiconductors it is having non-uniform concentration, non-uniform charge carrier concentration. So because of this non-uniform charge carrier concentration, that means this is the semiconductor, the charge carrier uh, concentration will not be uniform throughout the semiconductor material. Okay, so somewhere it will be having higher concentration, somewhere it will be having some lower concentration. So if we consider a level, so suppose this is the point, if we check what is the total number of charge carriers moving from this location to here and here to here, so overall we can find like the charge carriers, there is a movement in the charge carriers across this line or a plane, whatever plane we have considered for the analysis. So we will be observing a net flow of charge carriers basically from higher concentration to lower concentration. Okay, so this concentration gradient, like concentration gradient means whatever the charge carrier concentration is there at particular location or with respect to distance. Suppose this is the distance dx, with respect to distance dx we can see there is a difference in carrier concentration, so that is called a concentration gradient. So that basically diffusion occurs because of non-uniform nature of the charge carriers present in the semiconductors. Okay, so here because of this non-uniform nature of the charge carriers, there will be a concentration gradient. So concentration gradient is basically represented by whatever charge carriers are there divided by in what particular distance. So per distance, what is the concentration of this charge carriers is called the concentration gradients. That means that concentration will be depending with respect to the distance. If this is the distance x equals to 0, this is x equals to 1. So from moving from 0 to 1, there will be change in carrier concentration. So that is with particular distance, whatever the charge carrier concentration is there, that is considered concentration gradient. So in case of like holes are there, so in case of holes are represented by P. So change in holes per unit distance, you can say in dx distance, what is the uh, change in hole concentration is there, that is called concentration gradient. Okay, so here, because of this non-uniform nature of the semiconductor charge carriers, there will be a concentration gradient. This concentration gradient will be resulting in movement of charge carriers. So these holes will be moving because of the concentration gradient. So that means at one location charge carrier is P1, at another location it is P2. So because if P1 is at higher concentration, so there will be a movement of holes from P1 to P2. So that is defined because of the this concentration gradient. So one of the questions that can be asked in objective is, what results this diffusion? Why diffusion is resulted, or we can call cause of diffusion. So the cause of diffusion is the concentration gradient. If there is a concentration gradient, that only resulting the diffusion. If there is no variation in the charge carriers, if the charge carriers are uniform, there will be no diffusion. Okay, so if any material is there that is having the equal distribution of charge carriers, then there is no concentration gradient. Okay, so if there is no concentration gradient, there will be no diffusion. Okay, so also this concentration gradient basically results in the movement of charge carriers. So as there is a movement of charge carriers, there will be a current conduction. Okay, so if charge carriers are moving from one location to another, that will be resulting into the current conduction. Okay, so this concentration gradient is having the movement, results in movement of charge carriers like electrons and holes. Okay, so this movement of electrons and hole will result in the current. This current is called diffusion current. If this current is resulted because of the concentration gradient, this current will be called diffusion current. In the previous, we have seen like we are applying the electric field. We were applying the electric field. Okay, so with respect to this electric field, we were getting J, that is current density, is equals to in that case was NQVD or NQ mu E. So this was the current density, like the current flowing per unit volume. So that is depending on the electric field. That means if any semiconductor is there, on that we are applying electric field, there will be a current density, or there will be a current generation because of the movement of uh, carriers, charge carriers, electrons and holes in presence of electric field that is having a velocity Vd, that is drift velocity, and this drift velocity will be making the charge carriers move from one location to another location, and that movement of charge carriers because of the electric field is called the drifting of the charge carriers. So because of that drifting, there is a current that is called drift current. So in the previous lectures that we have gone, that is basically the drift current that results in drift current. Okay, so one of the type of current that flows in semiconductor is drift current, and another one is diffusion current. Okay, so overall we can conclude like we are having two different type of current flowing into the semiconductors. So the total current will be the addition of drift current as well as the diffusion current. So we will now see what is the expression for a diffusion current, and also in case of drift current we have already seen. So we will see like how the diffusion current is basically defined. So this is the semiconductor we have considered. In that, there is high concentration of holes at x equals to 0, as we are moving from x equals to 0 to a positive direction of x. Okay, there will be a decrease in concentration of the holes. So as we are moving from higher concentration to lower concentration, there will be a movement of holes from higher to lower. So as the holes are moving from x0 to some x value positive direction, there will be a current flowing. So it will be resulting into a current. That current will be in the direction of positive direction of x-axis. Okay, so this current that is resulting because of the holes, so we can call it ip. Okay, that is the current because of the hole. So this current will be having some current density with respect to the volume, so that is current density is jp. We can represent that current density that is in the positive x direction. Okay, so this jp, suppose this jp is the diffusion hole current density. Okay, so this is current density, so its unit will be ampere per, it is current density, so it is ampere per meter square. Okay, so current flowing per unit area. Okay, and also this current current density will be depending on the concentration gradient of holes. This is given by the diffusion process or diffusion. Okay, so if we replace this proportionality constant, this jp, that is the diffusion current uh, density, basically in case of current that is resulted because of the whole movement, holes movement. Okay, so that will be given by like it is equals to q into dp. Okay, so this is a negative. So this is the current density in case of uh, holes having a diffusion current. So this dp, that is the proportionality constant. So dp is called diffusion coefficient. Okay, so this is dp, that is called diffusion coefficient, or we call it diffusion constant. Okay, its unit is meter square per second. This diffusion coefficient, that is dp, so p stands for hole, so this is diffusion coefficient for holes. If in similar case, if we go with the electron as a concentration, that is diffusion is taking place because of the electron concentration gradient, that will be dn. So also this jp will be replaced by jn. Okay, so this is the proportionality constant, that is a diffusion coefficient or diffusion constant we call it. And this negative sign indicates the value like this jp, the current density should be a positive, but this dp by dx, that is whole gradient, is basically, as we are moving in positive x direction, that means if x is increasing, the whole concentration is decreasing, that means dp by dx will be a negative value. Okay, so to make this current density positive, we have made an extra z here, extra minus here. So okay, so this jp will be minus q dp by dp by dx. Okay, so this was the case in case of the holes as a carrier that is having going through the diffusion process. Similarly, for electrons, this electron density or the current density in case of electron, that is Jn, can be represented by Q dn by dx. Okay, so this is the case of electron as a carrier that is going through the diffusion process. Okay, and if we combine the overall, we can see like the total current density in case of diffusion, such that the electrons and holes both are the charge carriers. We can have the total current density in case of the diffusion is like Jp plus Jn. That will be the total uh, current density in case of the diffusion. So this is the only case of diffusion, or we can call it in case of diffusion. Okay, and also we have seen the current density in case of drift. So in case of drift, we have seen the similar. So here we can put the diffusion. The similar current density we can get in case of the drift also. And in case of drift, we have seen that in case of drift, the formula of the current density is NQ VD is there. Okay, so overall, if we want to find out the total current, that is I total in case of semiconductors, because in semiconductors, okay, so in semiconductors, we know the charge carriers are holes as well as electrons. So there will be a drift current because of holes and electrons also, and there will be a diffusion current because of holes and electrons. Okay, so if we find out the total uh, current, so that total current will be given as the I because of the drift plus I because of the diffusion. Okay, so this drift is caused basically because of the potential gradient, because of the potential gradient, because as we have applied the electric field, there will be a potential difference. Okay, so that potential difference means there will be a potential gradient. So this electric field is basically going to cause the potential gradient, and this potential gradient will be causing the charge carriers to move from one location to, or one position to another position, that will be resulting into the drift current. In case of diffusion, this diffusion is because of the concentration gradient. So this concentration gradient is because of the concentration difference, or you can concentration gradient is uh, or you can call it concentration uh, or instead of concentration we can say like it is because of non-uniform concentration. Because of non-uniform concentration, there will be a concentration gradient, and this concentration gradient will be causing the diffusion. Okay, so this is the total current in a semiconductor. So if we put the value into this, we can get the I total, or basically this current that is obtained is given by basically the current density. So whenever we go with the current, that current is basically defined by the current density. So in that case, this concentration gradient and potential gradient is causing the drift and diffusion current, and this total current will be given in terms of the current density. Okay, so in overall we will be finding out the current density, that will be the total current density is current density because of the drift plus J because of the diffusion. Okay, so again we can separate it out. In case of this, J total will be like the J because of the holes and J because of the electrons. So this J is basically J, P and Jn are constituting the drift as well as the diffusion. Here also it is drift and the diffusion. So we can write the Jp, that will be indicating the diffusion and the drift current. Okay, so Jp in case of drift is given by, like, because of the holes it will be Q, the formula was NQVD. Okay, so this N was the case when the only electrons are there. Okay, so now here the holes are also there. Okay, so holes and electrons both we need to find out. So here this diffusion in case of the holes and drift in case of holes is given by, like, instead of P N we will be writing P because we are talking about the holes. Okay, so P Q V D, this will be the drift, plus after a drift we can find the diffusion. So this is the diffusion is given by, like, in the above we have seen, in case of diffusion, this diffusion is given is minus Q dP. So it will be like minus Q dP by dx. So this is your diffusion and this is your because of drift. Okay, so similarly we can find out Jn, that will be given by, like, NQVD, and then next one is the diffusion. In case of electrons it is Q dN. So this was in case of holes, this is in case of electrons, so dN del n by del x. Okay, so this is the current density because of the holes, this is current density because of the electrons. So total, by adding these two we can get the total current density. So that will be the total current density because of the drift and diffusion. So overall that will be the case. And suppose we want to find out the current basically. So here in case of diffusion, if we know the Jn value, that is Q dN del n by del x. If we want to find out the current In, so that In will be the Jn, and Jn is given by, like, current per unit area. So I will be Jn multiplied by area. Okay, so once we know the area, we can multiply this current density by area, we can get this diffusion current. Okay, so similarly in case of holes also, once we can multiply with the area, we can get the current because of the holes, and by adding these two we can get the total current. Okay, so this is the formula overall in case of the current if we are talking about. And also this diffusion, so generalized diffusion equation is basically we can just see. So generalized diffusion equation is basically given by, like, J diffusion is equals to minus q, whatever diffusion coefficient is there, dy by dx. And here, if this diffusion is because of the holes, if because of the holes are there, this charge carriers, this q will be replaced by uh, plus q, and if it is because of electrons, this q will be replaced by minus q. So here we will be replacing, and with respect to that we can put the value. So for holes, here we will be putting p, and here also we will be putting p, and this q will be replaced by plus q. And in case of holes, in case of electrons, if we want to find out the current density, we will be replacing this q with minus q. So overall it will be a positive in case of the electrons. In case of electrons it will be positive, okay, and here in case of holes it will be a negative. So total current, also we can define this total current. So the total current will be in terms of the current density only. So now we will some conclude some points, like how on what parameters this drift current and and diffusion current is going to dependent. Okay, so we can just write like, so if drift current will depend on what parameters. So this is the basically the component that is given by the drift current. So from there we can find, so the drift current will be depending on, first of all, n is there, n is the concentration of the charge carriers, basically either holes or electrons. So first of all, drift current will be depending on the carrier concentration. Okay, next one is Vd, and Vd is given by, this Vd is mu into E. Drift velocity is given by mobility into the electric field intensity. Okay, so this, if we put this value, we can find like the drift current will be depending on the mobility also. So this drift current will be depending on mobility of the charge carriers, and also the electric field. So basically it will be depending on the field intensity also. So this is the different parameters on which this drift current will be depending. But overall, if we say, this drift current will be mainly depending on the electric field only, because the electric field is the causing, you can say, parameter, causing agent for this drift current. So this drift takes place only when there will be an electric field intensity, or electric field is applied to a semiconductor. Okay, next we can see how or in what parameters basically this diffusion current will be depending. So the diffusion component is basically this one. So here it depends on q, that is constant, dp it will be a constant for a particular case. Okay, and this del p by del x, so this is the gradient. So the only parameter that it depends basically is the concentration gradient. It will be depending on the concentration gradient of charge carriers. Okay, it will be basically depending on the concentration gradient. So the next point we will see, that is relating this uh, diffusion coefficient and the mobility. So there is a relation called Einstein equation or Einstein relationship so the parameters like the diffusion coefficient and the mobility is dependent on a parameter and that is related with the term called thermal voltage or we can call it the carrier equivalent of the temperature we can represent in terms of Vt. So the relation between the drift velocity diffusion coefficient parameter. So this is basically diffusion coefficient like dp divided by uh, not this. So dp by mu p. So dp by mu p, that is diffusion coefficient in case of holes, divided by the mobility is equals to dn divided by mu n. So whatever the ratio in case of holes and electrons are there, that is equal, and it is also equals to the parameter called Vt. Okay, so is called this Vt is basically called volt equivalent of volt equivalent of temperature. That means if there is a temperature variation, then this with respect to that temperature variation, the ratio of diffusion coefficient and the mobility of in that particular case of the charge carrier either holes or electrons, that will be a constant. That means if we are increasing the temperature, with respect to that, the ratio of diffusion coefficient as well as the mobility is also going to change, and the change will be same in case of holes as well as the electrons. Okay, so this relation is basically called Einstein's equation. Okay, and this Vt is called volt equivalent of temperature, or it is also called as the thermal voltage. Okay, so this is like if we are changing the temperature, what will be the equivalent change in voltage that will be taking place in case of the semiconductor, that is given by the volt equivalent of temperature. Okay, so if temperature is being varied, it will be equivalent to varying of voltage in a semiconductor. Okay, so that's why it is called volt equivalent of temperature, and it is also called a thermal voltage. Okay, though this thermal voltage is basically defined by the parameter like called this kT divided by kT by basically q. So here k bar is Boltzmann constant, we can call it a Boltzmann constant. Boltzmann constant, and its value is given in terms of this value is given in terms of the unit called joules joules per degree Kelvin. Okay, so this is your Boltzmann constant. Okay, and also this Boltzmann constant is defined by another uh, parameter that is called k, and this is also the same Boltzmann constant, but it will be in terms of electron volt per degree Kelvin. Okay, so there are two Boltzmann constant defined, k bar and k. K bar is related with the thermal voltage, and the relation between k bar and k is like, so k bar is given by 1.6 into 10 power minus 19 into the k, because this k is in electron volt per degree Kelvin. So to convert this electron volt per degree Kelvin to joule per degree Kelvin, we need to multiply 1.6, that is q. Okay, to this k we will be getting k bar. So this K bar is basically its value is given uh, in terms of K and K multiplied by Q. It is like Q multiplied by K, it is equals to K bar, and here K is given by the value like 8.62 into 10 to the power minus 5 electron volt per degree Kelvin. Okay. Overall, we can just relate this thermal voltage or volt equivalent of temperature. After simplifying and putting the value, we can get is T divided by 11600. So this is the relation between the Vt and the temperature. That means Vt is directly proportional to temperature. We can just correlate from here, and also at room temperature, this Vt value is equivalent to 26 millivolt. Mostly in case of some numerical questions, if this Vt is being used, then mostly it is asked at room temperature only. So room temperature is 300 degree Kelvin. So at 300 degree Kelvin, the Vt value is 26 millivolt. Okay. So this is the Einstein equation. So next, we will see some numericals or some one more term is there. We need to just define. So in case of diffusion, another parameter is defined that is called diffusion length. Okay, it is represented by L. Uh, it is basically defined by L in case of holes and in case of electrons also. So diffusion length is there. So diffusion length in case of holes and electron it is different. So it is L P or Ln. So diffusion length in case of holes and diffusion length in case of electrons. So we will just see what is a diffusion length and how it is related with the different parameters. So once uh, we have seen here, like the because of the concentration gradient, the charge carriers are moving from one location to another location. Okay. Also, this length of diffusion or diffusion length is basically defined as the distance migrated by the charge carriers uh, in presence of a diffusion. Like once because of the concentration gradient, there is a movement of charge carriers from one location to another location. Okay, so that means the charge carriers are moving from one place to another place. So what distance these charge carriers are moving, that is called diffusion length. So that diffusion length will be depending on the diffusion constant, okay, along with the carrier lifetime. So in the recombination and generation we have seen, like if the covalent bonds are there between the atoms, so once this covalent bond breaks, okay, so a hole and a electron will be generated. So once these holes are electrons are generated, and again this electron travel inside the semiconductor and combine with a hole, and after combining the hole the recombination is taking place. So once the whole electrons have been generated and till it is going to be combined with another hole, whatever time it travels is called carrier lifetime. Okay, so for electron and for holes this carrier lifetime is defined. Okay, so based on the carrier lifetime, so for what time period these holes or electrons are available into the semiconductor. Okay, so that will be depending uh, on the parameter like the diffusion length. So diffusion length will be depending on the tau value. So whatever the carrier lifetime value is there, so that relation is related by, in case of holes it is lp. So this lp will be given as the relation like under root d into tau. So that is dp into tau p. Or in generalized, similarly in case of n, in case of electrons, this diffusion length is defined by dn tau n. In generalized form, we can just write L is depending on d into carrier lifetime. Okay, so this is the uh, formula for diffusion length. And in our some of the uh, questions, in objective type questions, this directly LP value is asked once carrier lifetime and diffusion coefficient is given to charge carrier. We can get the LP value, diffusion length. Okay, so that you can just relate like how this LP is depending with respect to the diffusion coefficient and the carrier lifetime. Okay, so it is given here for to remember you can just relate like on what parameters it will be depending. So first of all, it is a diffusion. This is defined in case of diffusion, so it will be depending on the diffusion coefficient. And also this, there is a length, diffusion length is there, so charge carrier is traveling a particular length, so that length, how much length it will be traveling, that will be depending on its time period, like for what time period it is available into the conductor. Okay, so this is the diffusion length basically. So just you can write tau here. D is diffusion constant and tau is your carrier lifetime. Okay, so these are the two different parameters on which it will be depending. So this is how defined. So just we will also check like on what parameters this length of diffusion or diffusion length depends. So diffusion length depends on, so as the formula says, it is depending on the diffusion coefficient and carrier lifetime. Okay, but from the above Einstein equation, we can just see this diffusion coefficient depends on mu p multiplied by, so separately we can find like dp is given by mu p into vt, or dn is equals to mu n into vt. Okay, that means the diffusion coefficient also depends on mobility as well as the temperature. Okay, so from there we can just note it like this diffusion length will be depending on the diffusion constant. Okay, diffusion constant and the mobility and the temperature as well as the tau, that is carrier lifetime. So these are the different parameters on which the diffusion length will be depending. Okay, so we will see some numerical questions based on this diffusion process, and also it is a generalized equations basically, questions basically. So suppose we have a question given like semiconductor is given, a semiconductor, a wafer of 0.5 mm thickness is given, that is applied with a potential of 100 millivolt. It is applied by a 100 millivolt potential across its thickness. We need to just find the electron drift velocity if the mobility is 0.2 meter square per volt second. Okay, so just in the first case, so initially we can write like what is given. So thickness is given and also potential that we are applying to a semiconductor that is having a thickness of this is 100 millivolt. So these two are the parameters given, and also in the first case it is asking for drift velocity, and that is for electrons. So for electrons, drift velocity it is asking for. So drift velocity is given by mu n into e. So mu n into e will be given by the drift velocity, and mu is also given 0.2 meter square per second volt second. Okay, and we need to find out the E first. The electric field is, okay, so this is how electric field is given, or we can call it like electric field is given by change in voltage, okay, or the voltage itself, potential. This voltage is potential divided by the distance. So here 100 millivolt divided by 0.5 millimeter. Okay, so we can just see it will be like 1000 divided by 5 volt per meter is equals to 200 volt per meter. So electric field is 200 volt per meter. So once we have found out the electric field, we can find the drift velocity. Okay, so drift velocity will be mu into E. So mu is given 0.2 meter square per volt second multiplied by electric field, that is 200 volt per meter. So volt and volt it will cancel out, 1 meter and 1 meter will be cancel out, so it will be Vd. So this Vd will be given like 40 meter per second. Okay, so this is the drift velocity. The next second case is we need to find out how much time is required for electron to move across the this thickness. So how much time this electron will be taking to move to this thickness. So thickness is given, so 0.5 millimeter. We need to find out like how much time it will be taking from moving from this location to here. So the time in the second case, we need to find out the time. This time will be given by total distance, whatever distance is there, divided by the velocity. Drift velocity we have already found out the value. This is 0.5 millimeter divided by 40 meter per second. So from there we can find out the time. It will be coming out to be 12.5 microsecond. Okay, so this was the simple question. Similarly, we are having another question like at room temperature the volt equivalent temperature is given like Vt. So this Vt is given, whole mobility is this, mu p is given 500 meter square per volt second, and carrier lifetime tau p is given 130 nanosecond for the sample of, okay, so here n type semiconductor is there. In that case the carrier lifetime and whole mobility is given in case of n type. What is the diffusion length? So we need to find out the diffusion length. Okay, so here we just need to find out the diffusion length. So to find out the diffusion length, basically what we need to do is we need to find out the diffusion coefficient, and also we need to find out the diffusion coefficient at the carrier lifetime. So carrier lifetime is already given. Okay, so we have been given the carrier lifetime and we need to find the diffusion coefficient. So this diffusion coefficient by using the Einstein equation is given like dp will be equals to mu p into Vt. Okay, so from there we can find out the dp, and we already have the tau p. So diffusion length or LP will be given by under root dp and tau p. Okay, so from there we can find out the diffusion length. So just we need to find out this by using this value. So Vt is given and mu p is also given, but multiplying we can get the dp, and from there dp is available and tau p is available, we can find out the lp. Okay,